Alright, let's talk about metal acidity. This particular form of acidic behavior has its origins through something we call induction. And the idea is that the metal center with that positive charge is attracting the electrons of the ligand. So let's say in the case of the hexa aqua complex, which I've decided to spell out one of the OH bonds in each one of the waters, the electrons get attracted towards the metal center. And ultimately what happens is that the H at the end of the of the water molecule ends up having its electron density depleted. And the higher the charge of the metal is, the stronger the attraction is towards the metal, thus leaving the H more and more naked. And that action allows the hydrogen to basically be free to leave as an H plus. So in the process, you end up forming a water, you're taking a water molecule that's bound to the metal and turning it into a hydroxyl ligand while expelling out an H plus. So this allows the manganese center to behave in the same manner that Brownstein and Lowry depicted for a particular acid. And this is all based in terms of Coulombic attractions, right? The metal center with a positive charge is attracting the electrons with negative charge. So this all bears the idea of Coulombic forces, which the force of attraction, of Coulombic attraction, is given here by the formula. Charges multiplied by each other divided by the distance square of the two particles. And that idea of the charges, multiplying each other, if you concentrate on the metal, right? So here we're having neutral ligands. So if you concentrate on the metal center and simply square the charge of the metal and divide it by the radius of the metal, you can actually find out how acidic a metal can be, right? So in essence, we're going to be focusing on that and say, okay, the force, by the way, is divided by the square of the radius, whereas the actual energy, which is technically the integral of this force as a result of changes in distance, can be given by the charge squared divided by r. And then the rest of the stuff is just a collection of constants. So what we're going to do is kind of take a look at this charge square over r and see what it tells us in terms of the metal. Alright, so let's see what this ultimately says. Okay, so if you recall from previous lectures, we have a table of ionic radii that basically is given for the vast majority of the possible charges that different elements can possess, right? And so you can definitely focus on the transition metals to depict what's going to happen. Well, we could also include even the lanthanide, actinide metals, and even the main group metals that are present in the periodic table. All right, now in terms of electronegativity, there's something interesting too that happens. The acidity does increase with electronegativity, and we saw that when we looked at the trend going from left to right. And there's going to be a key value that we have to be on the lookout for, and the value is about 1.8. So if your metal hits an electronegativity of 1.8 or above, you're going to end up using one specific formula to calculate the overall pKa of your metal. But if you have a pKa that is below that, then you use a slightly simpler version of a formula. Right, now the values or the metals that have electronegativity values that technically fall at 1.8 or above rely on the ones that I highlighted here. Probably the one exception is zinc. That one doesn't exactly make the cut. I included it there just just because, but technically it doesn't quite make the cut. The rest of the elements though, which the majority of them lie on the second and third row of the periodic table, for the transition metals at least, those are the ones that make a difference in the equation. So this is the way it goes. For the metal cations, if you have a cation that has an electronegativity value less than 1.8, the pKa is approximated as being 15.14 minus a constant 0.8816 times the charge squared divided by the radius. And if you have an electronegativity value that is higher than 1.8, then the correction to the formula is that in addition to the C squared over R, we're going to add 9.6 times the electronegativity of the metal minus 1.5 prior to multiplying by 0.8816. Alright, and so to give you an idea, and this is kind of a reference that you can use to kind of guide you. If the C squared over R value is less than 1, and by the way, the radius here has to be in angstroms, but if this value is less than 1, then you're dealing with a cation that is considered non-acidic. You can add it to water, but you don't expect it to change the pH, right? And so the alkali metals like sodium, potassium, rubidium, and cesium, silver 1, gold 1, and thallium 1, you don't expect those particular cations to make the solution acidic. But then when you start looking at values that range between 1 and 4 for C squared over R, you get into the feebly acidic elements. So calcium, strontium, titanium 2 plus, copper 1 plus, silver 1 plus, 2 plus, excuse me, palladium 2 plus, europium 2 plus. These elements have a small tendency, it's not very high, but it's a small tendency to acidify the solution. So if you add them to water, you'll see a tiny little drop in the pH. Then you get to the ones that are weakly acidic, the values of C squared over R that fall between 4 and 10. And this actually is where the vast majority of the elements, especially in lower oxidation states, the 2 plus state, as you can see for the lighter metals, and the 3 plus state for the bigger metals, these are the weakly acidic metals. And if you add them to water, you will see a drop in the pH that is moderate in scope. And speaking of moderate, then we get to the moderately acidic metals, the ones that have values of 10 through 16 for C squared over R. And these ones generally are the lighter elements with a 3 plus oxidation state, or the bigger elements with a 4 plus oxidation state. After that, you get to the strongly acidic metals. If you drop any of these metals in water, you will see a significant drop in the pH. And these are the 4 plus metals, which are lighter, generally speaking, that the ones that have lower atomic mass, or the ones that are bigger that also with the 4 plus oxidation state can actually depict that particular aspect. So if you drop in water, you expect to see the drop in the pH to be considerable. And then there are the ones that are very strongly acidic, values that are higher than 22. And those ones in general will be light elements or even bigger elements that have oxidation states that are 5, 6, 7 plus in general. Alright, so let's see exactly how this plays out. Now, for the anions also we have a formula that also applies to their anionic radii, but since we have only a handful of anions, we're very rarely going to use the pKb formula. For the most part, we're going to stick to the pKa. Right, so this is just a handful of ions that you can take a look at. So it's not the most helpful, but maybe I'll use it once or twice in the context of this lecture. Okay, so let's do a few examples. Alright, so we're going to determine the acidity of nickel 2 plus. Okay, nickel has an electronegativity of 1.91, which means that we're going to have to use the second version of the equation. So what we do is we input the 1.91 electronegativity in the parentheses, so we subtract 1.5 from that value, then we multiply by 9.6. Okay, so 1.91 minus 1.5 is 0.41. Multiply that by 9.6, that will give you 3.936. Now what we need to do is input the charge of nickel. The charge of nickel is 2 plus. 2 plus squared will give you 4. And we divide it by the radius of nickel 2 plus, which is 0.83 angstroms. Okay, so we input that. And we basically divide 4 by 0.83. And to that answer, we add 3.936, which gives us 8.755. Multiply that by 0.8816. And subtract it from 15.4, and you find out that the pK of nickel 2 plus is about 7.42. And what this is basically telling you is that, yeah, this is weakly acidic, but it's not going to precipitate. And the reason, or rather the rule of thumb that you can use is the one that I'm going to depict in a little bit. Um, it has to do with the pH of water and the pKa that we're getting for the metal. So let's take a look at iron 3 plus and see what we get for that. Okay, for iron, the electronegativity is 1.83, so we're going to use the second equation again. Okay, so we have 1.83 minus 1.5, which is 0.33. Multiply that by 9.6, we get 3.168. Charge of iron is 3, we're going to square that to get 9, and the radius of iron 3 plus is 0.78 angstroms. Okay, so we input all of that in the equation. 9 divided by 0.78 plus 3.168 is 14.706. Multiply that by 0.8816 and subtract it from 15.14, excuse me, you find out the pK is 2.03. Now, the thing about this is that you gotta remember that you're adding the metal ion to neutral water that has a pH of 7. So if the pKa of the metal is below 7, what this is telling you is that the metal is acidic and is going to generate some protons. Alright, so this is the way you ought to think about it, right? So we found the pKa value for the metal. So because it's below 7, you're going to be donating a proton to water. This is basically the first pKa in the series. And once again, you base it on the pH. If you're below the pH of water, which is 7, you're going to generate protons. And then you can ask, what about second dissociation? Can you dissociate a second time or even a third time? And now here's where a very rough idea of whether this can happen or not takes place. So if the metal is still, iron 3 plus, by the time you remove a proton, the overall charge that you're going to get will be 2 plus. So if that is to undergo a second dissociation, the charge will go down to +1. And then we kind of have to do a little addendum to this. Okay, so yes, we have the charge of the metal that was 3 plus, but now the overall charge is going to be 2 plus because of the presence of the hydroxyl ligand, right? And so this changes things a little bit. The pK now ends up, going above 7, so you wouldn't necessarily expect this thing to dissociate any further. So the first one is definitely in favor because it falls below a pH of 7. The second one, not so much. And so the third one, yeah, it's probably not going to happen. Now, a much more rough estimation of the pKa's, which I tend to use, but I gotta tell you, it's pretty rough, is that if you end up with this C-square over R value that falls between 16 and 22, you're probably going to form a precipitate when you add the metal to water. And the way you kind of tell for sure that this is going to happen is you first calculate the pKa based on the formula, which depends on what the electronegativity value of the metal is going to be. And then what you do is you determine how many pKa's you have to go through to make the entire complex neutral, and that basically depends on the charge of the metal. If the charge of the metal is 3 plus, you have to go through 3 pKa's to make it neutral. If the charge of the metal is 2 plus, you have to only go through 2 pKa's to make it neutral. So to estimate what the final pKa is going to be, I have a very rough formula right here. You use the first pKa that you calculate using the equations, and to that pKa you add 3 times n minus 1, where n is the charge of the metal. And the idea is that if this final value falls within 1 and 7, then that means that you're going to precipitate a complex, because the final pKa will be acidic enough that you will remove that last proton that will turn the complex neutral. And once the complex becomes neutral, it will crash out from solution as a precipitate. So let's take a look at iron 3 plus once again. We calculated the value of the pKa to be 2.03. So if we use the rough approximation, the charge is 3 plus, so we're going to change or replace n by 3. 3 minus 1 is 2. 2 times 3 is 6. And 6 plus 2.03 is the same thing as 8.03. Since the pK is not between 1 and 7, what this tells you is that iron 3 plus will not precipitate. It will remain soluble in solution. So this is a kind of very rough but helpful way of figuring out whether taking a particular ionic complex is going to generate a precipitate or not, because you don't want to go try to make a solution and then find out that everything is crashing out from solution. That's not going to help you in your chemistry. Alright, so in the next video we're going to talk about formation constants and equilibrium calculations of the formation of complex ions. So see you in the next video.